right. Can you hear me and see my screen?
Yep.
All right, cool. All right. So today we're continuing going through our unit about derivatives. We're going to be finishing the slideshow from day 6 and starting the slideshow from day 7. And we're going to be introducing some final new derivative topics. And then tomorrow we will finish our unit on derivatives and possibly start unit 4, which is just applications of derivatives. So it's just a natural continuation of unit 3. All right, so we've gone through all this. We've gone through the topics of discussion. We've gone through the first couple slides. The slide we left off on was this slide. We finished this slide, right?
Yeah, I think so.
Cool.
Yeah.
Cool. All right, so the next slide talks about this thing called Leibniz Notation, which I've written down here, and I'll explain what it is in just a second. And all Leibniz Notation is a different way to express the things we've been talking about. And I'll go to a Jamboard to explain what I mean by that. For example, when we wrote what the chain rule was, remember we wrote that the derivative of f of g of x was equal to f prime of g of x times g prime of x. All right. This is the way we wrote the chain rule. We wrote it in this notation specifically. If I go back to the slideshow, this is how you write the chain rule in Leibniz notation. So obviously there's a different way to express the chain rule, and it's probably useful to go over in case you ever see this notation used in a textbook or a problem. All right. And it will become useful when we start doing some integral stuff. Leibniz notation becomes useful. So it's important to learn what it is. All right, so in our regular notation, which I'll call it regular notation, I think it's called Newtonian notation, but don't quote me on that. I honestly forget what the exact thing is. But so I'll just call it our original notation. In our original notation, we described or we wrote functions as either y or f of x, right?
Yeah.
In Leibniz notation, for some reason, and I'm going to explain why I hate this in just a second, in Leibniz notation, we express functions as u or v. So if you see u or v, that just means a function, like f of x or y.
And so those would normally be like two different functions.
Yeah, exactly. So You'll see why this gets annoying in a bit. There's a Leibniz notation for the product rule. Here, I'll just Google it and show you what I mean. The problem with using v's and u's, I find, is that it's often really hard to distinguish between the two of them.
Yeah, I can imagine that.
Yeah, so it's frustrating. I can't find it here, but definitely when we get into our unit on integrals, there's a rule that uses u's and v's. We describe it with Leibniz notation, and it's really frustrating because when I'm drawing it, like I have to really be careful with my u's and really be careful with my v's just to make sure that we're not mistaking anything.
Okay.
All right. Okay. So as a recap, with Leibniz notation, instead of writing y or f of x, we express functions as u or v. And additionally, we still express the slope or the derivative as dy over dx. That might be a little confusing, but when we're talking about the chain rule specifically, we're talking about many functions, right? There's many functions at play. There's the composite function that's at play. There's f of g of x at play and g of x at play. So there's two functions at play. We call the main function, the one we're talking about, we call it y still, because it's the main function we're considering. So we call it like we normally do. We say it's y. All right. But any other functions that we're dealing with, we'll label as u or v. So in Leibniz notation, we describe g of x as either u or v. You can think of it as the supplementary or non-main functions we describe with u and v, and the main function we describe with y still.
Okay, yeah, that makes sense.
Okay, cool. So if we go back to this slide that writes the chain rule in Leibniz notation, here. Actually, before I do this, I want to explain one very quick concept. I know I'm going all over the place, I tried to plan out today as best I could, but it's a little all over the place, so I apologize for that.
No worries, no worries.
Cool. I just want to make sure we're all on the same page. When I say the following phrase, when I say the derivative of y with respect to x, all right? All that means is I'm asking how quickly what is the rate of change of our function y with respect to a change in x? Do you kind of see what I mean? Do you see why I would say
that makes sense?
Yeah. So whenever I say the derivative of y with respect to x, that's what I mean. We're taking the slope of the function, which is y, with respect to our input x.
Yeah. Okay. Like as you change x, what happens to the derivative?
Exactly. What happens to the function as you change x, right? And that question, if we want to ask what happens to our function as we change x, the derivative is going to tell us what happens. So if we ask what happens to y as we change x, we're finding the derivative of y with respect to x.
Okay. Yeah, that makes sense.
Okay, cool. All right. Additionally, I want us to be familiar with this idea. All right. You could imagine the function f of g of x, right, as our machine, right, where we have a function f that takes in g of x as inputs and spits out f of g of x.
Yeah.
All right, cool. So let's say f of x was x squared. All right. If I were, and this concept might be unfamiliar to you, but we're gonna make it make sense. If I graphed f of g of x as my outputs and g of x as my inputs, all right, instead of f of x being instead of just x being my inputs, g of x are my inputs. If f, the function f, takes in inputs of g of x and squares them, right?
Yeah.
Then if we graph f of g of x with respect to g of x,
is that just the same as x squared?
Exactly. It's going to look like the graph of x squared.
Gotcha. Yep.
So even though the idea of making a function your input might seem weird, I hope at least the idea of graphing f of g of x with respect to g of x will just produce whatever the function f is.
Yeah, that makes perfect sense.
Cool. Awesome. So additionally, I think we did this on a later slide in day 7, but it was actually like nagging at my brain before this, and I really want to get it out of the way. I want us to go back to the chain rule and rederive it using this concept because it's really important to understand. Because correct me if I'm wrong, the idea of taking the derivative with respect to g of x probably seemed weird before today.
A little bit, yeah.
Exactly. So we're going to try and make it make sense with this example, all right? So, all right. If I were to ask what happens, all right. So we can imagine f of g of x as a big machine, right? That takes in x as inputs. It goes through the g function to get g of x. And then it goes through the f machine to get f of g of x as our final output. All right. So if I asked, well, how much is our output changing if we change our x value? I think you'd agree with me that we have to consider how much it changes through the g port and how much it changes through the f port.
Yeah.
All right. So let's graph these two functions individually. All right. This g function takes in x as inputs and spits out g of x as outputs, right? That's what it describes. So we could draw a graph like this, and I'll just draw some random function. All right. Now our second function f takes in g of x as inputs and spits out f of g of x, right? What the hell did I do? All right. So we could graph it like this, where we have f of g of x as our output and g of x as our input. And the graph of this function will look identical to the graph of f of x, right?
Yeah.
Do you kind of get why that works? Because we're taking g of x as input, so f of g of x is just the same thing. Because our input...
That makes sense.
Yep. Okay, cool. All right. So... All right. So if we want to ask what the rate of change of this function is, all right, would you agree that if I wanted to find the derivative, I'd take a tiny change to f of g of x and divide it by a tiny change to g of x? That's the definition of a derivative.
Yeah.
Cool. But the problem is the derivative written in that way doesn't tell us the derivative of f of g of x with respect to x. It tells us the derivative of f of x with respect to g of x. And we want a derivative rule that will tell us how this function is changing with respect to x, not g of x. Does that kind of make sense?
Yeah, I'm following that.
Cool. So we can do a little a thing with our function over here to try and figure it out. So if I asked to find the derivative of g with respect to x, right, I would take a tiny change to g of x, dg of x, and divide it by a tiny change in our input, dx. Right?
Yep.
So if I wrote that dg of x divided by dx equals the derivative of g of x, you'd agree with me, right?
Yeah.
Cool. So this is actually really useful, right? Because we could rewrite dg of x as g prime of x times dx, just by multiplying both sides by dx.
Yeah.
All right. So if I said that the derivative of f of g of x is equal to a tiny change in f of g of x divided by a tiny change in g of x. Remember we said that from our very original function?
Yep.
All right. But here, I had this in my head earlier, and I just need to make sure I'm getting this right. All right. So would you agree that this, we could rewrite this as the derivative of f with respect to g of x?
Yeah.
Cool. So that's all we mean when we say this. When we write that f of g, the derivative of f of g of x is a tiny change to f of g of x divided by a tiny change in dx, we're taking the derivative with respect to our input, right? If we had f of x, if we were graphing with respect to x, our derivative would be f prime of x. It's the derivative with respect to our input.
Okay.
So when our input is no longer x and it's instead g of x, we just have to replace x with g of x because that's our input now.
Okay, that makes sense.
All right. So what have I done? I remember doing this in my head earlier and it worked. So I might have screwed up a tiny bit, but that's okay. Actually, yeah. I'm having a little brain fart moment. I remember that I did this morning and I got it perfectly, but now I'm forgetting exactly where to go from here.
No worry. I mean, we can also do something else, and then if it comes back to you, we can always come back to this. I'll be able to remember where we're at.
Okay, let me approach it in a different way and see if that solves the problem. All right. So we could say that the derivative of f of g of x equals the tiny change to f of g of x divided by a tiny change in g of x, right? From our original function.
Yeah.
Cool. I'm going to multiply both sides. I'm just going to say that the derivative of f of g of x, I'm just going to because it's hard to write, I'm just going to write it as u. All right. Just because it's annoying to write this out the whole time, I'm just going to say that I'm going to write this as u instead.
Okay. Yeah.
I don't know if calculus people actually do this, but I'm just doing it for simplicity.
Sounds good.
So I'm going to multiply both sides by dg of x. U dg of x equals df of g of x. Right? But remember from our previous slide, we said that dg of x is g prime of x times dx.
Yeah.
Because we just took, we know the derivative of g with respect to x is this. So if we multiply both sides by dx, we get dg of x equals g prime of x times dx. Cool.
Yep.
So let me just replace that in this. Let me just replace dg of x with that. All Oh, okay, now I know where I'm going. Sorry about the hold up at the beginning.
No worries.
All right, so I just need you fine with what I've done so far. The idea of like all the substitutions I've done, the idea of finding the derivative of a function with respect to like g of x, for example. It's just we're using g of x as our inputs instead of x.
Yeah, that makes sense.
Cool. All right, so I'm going to divide both sides of this equation by dx. All right, and I want you to tell me, what does this side tell us? What is this side representing?
Derivative of f of g of x.
With respect to x.
Yeah.
Which is what we wanted to find originally. The problem with our original thing is this is the derivative of f of g of x with respect to g of x, right?
Yep.
And we know that this is just going to be the graph of f of x, right?
Yeah.
Remember we said that? But we know that if I graphed like sine of x squared, for example, it's not going to look like sine of x. It's not going to look like f of x. So clearly, the derivative with respect to x is different than the derivative with respect to g of x.
Yeah, definitely.
So this will not be our final answer. But look here. We have the derivative of f of g of x with respect to dx. That's what we're looking for, is equal to u times g prime of x. But what is u? U is this. We said u is this, but then u then is also equal to this because we had this equation. All right. So I want you to tell me, what is this representing?
That's the derivative of f of g of x with respect to g of x.
Exactly. So I could rewrite this as f prime of g of x. Do you see how that notation is the same? It's the derivative of f with respect to g of x times g prime of x, because we have to multiply it by g prime of x. Do you see how that is then the chain rule?
Yeah, I do.
Okay. Cool. So you can be honest with me. Does that kind of clarify the chain rule a little bit? Do you kind of understand it a bit more?
A little bit, yeah.
Cool. So yeah, I just wanted to clarify what we mean when we say we're taking the derivative of a function with respect to another function. It just means we're treating a function as the inputs to some other function.
Okay. Yeah, that makes sense.
Cool. Exactly. So then the slope here would be the derivative of f of g of x with respect to g of x.
Okay. Yep.
Which we could denote as f prime of g of x.
Perfect.
All right. And remember when we found, like, for example, at the very beginning, we found the derivative of x squared, right? We said that it's the derivative of x squared with respect to our input is twice our input. Do you see what I'm saying?
Yeah.
So if we found that the derivative... So if we wrote this, if we found that the slope here was 2, wait, actually, let me backtrack. If we found that the slope of this, let's say this function is x squared. It looks like x squared, right? That means that the slope is twice whatever the input is, right?
Yeah.
But what's our input here?
Wait, what?
So if f of x, so if we're graphing f of g of x with respect to g of x, if g of x is our inputs.
Oh, right. Gx is the input.
Yeah, so g of x is the input. So the slope of our function would be twice whatever the input is. X, yeah, right? 2 times g of x.
Cool. That makes sense.
So that would be f prime of g of x, right? It's just, we know our derivative of x squared is 2x, but because our input is no longer x, we have to put a g of x in there because that's our new input.
That makes sense. Yeah, it's just like once removed, but it's like the same thing. That
makes sense. Cool. So that was a long way of explaining the chain rule, and I think we're gonna get to it. Can you hear me, by the way? Did I mute myself? Oh, I think I muted myself in accident. My bad.
Yeah, I don't know how you did that. You're good though.
Okay, so that was a long tangent in explaining derivatives with respect to not x but other functions. But I hope that at least makes a little bit of sense. It just means
it definitely does.
Cool. Awesome. So Leibniz notation is just expressing that in a different way. All right. For example, the chain rule in Leibniz notation, we say our big function is y, f of g of x. All right. So dy over dx, you can see, is the derivative of f of g of x with respect to x.
Yeah.
You see that in Leibniz notation. All right. And how we write it in Leibniz notation, let me just make sure I'm getting it right, is we say that it's equal to dy over du times du over dx. And u is g of x. All right. So if u is g of x, can you see how dy over du is the derivative of f of g of x with respect to g of x?
Yeah.
So that's the same thing as f prime of g of x, right?
Uh-huh.
And you see how the derivative of u with respect to x, if u is g of x, is just g prime of x, the derivative of g with respect to x.
Yeah, so then you just get the chain rule that we like.
Yep, exactly. So do you see how Leibniz notation works? Could you read this and understand what it's saying now?
Yeah, I do.
Cool. And what's another cool nifty trick? Here's a reason why Leibniz notation works. When you multiply these two things together, you're going to get a du on the top and a du on the bottom, right?
Yeah.
So you get dy over dx equals dy over dx.
Perfect.
Cool, right?
Yeah.
So Leibniz notation also helps you see why the chain rule is valid too.
Okay, cool.
Because Leibniz notation emphasizes the idea that du and dy, they're like tiny nudges to our function, right? The derivative is a tiny change in y divided by a tiny change in x, or a tiny change in our output divided by a tiny change in our input.
Okay, yeah.
Right? And Leibniz notation is emphasizing that. So for example, if we graphed f of g of x with respect to g of x, dy over du is just the tiny change in y divided by the tiny change in our input, which is g of x. All right. So Leibniz notation is really emphasizing the idea that all derivatives are is tiny, is calculating the slope with very tiny numbers. So because these are still tiny numbers, you can kind of still treat them like numbers. And that's why you can do the division thing, the canceling out.
Okay, cool. Yeah.
Awesome. All right. So that's Leibniz notation. So what I need you to find with is the following concepts. Taking the idea of taking the derivative of a function with respect to not x, but another function.
Yeah, I'm cool with that.
And reading Leibniz notation. You could tell me what this means. The derivative of y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x. It's a very long way of saying the chain rule.
Yeah, I think I got it.
Okay, cool. Awesome. And if we need to refresh it later, we can do that.
Sounds good.
Cool. Awesome. All right, so that is that. The next slide returns to the chain rule. It's the formal chain rule written in the textbook, and I figured that we could go to it and just make sure that we understand it from the textbook. Because if you read the textbook definition and you understand it, that means we understand the chain rule and we're all good to go. All right?
Yeah.
So this textbook mentions something, all right? And I need to reiterate it. All right. So remember, we said that if we had some function, f of x and dx, all right? If it was not differentiable at that point, if we picked a point and it was differentiable there, you'd agree that f of x, just getting started, I'm still warming up to the day. You'd agree that if the function was differentiable here, then this ratio would have to be a number. It'd have to equal some number.
Yeah.
Right? That's the definition of a derivative.
Yeah.
All right. So we'd say then that if the function is differentiable here, right, it's differentiable at some point x. Cool. So if we graphed f of g of x with respect to g of x, all right, can you see that if I picked some point like here, all right, it would be differentiable at it would be differentiable at some point g of x.
Yeah.
We wouldn't say that this point is x, but rather it's g of x.
Yeah, that makes total sense.
Okay, cool. So when we go to the textbook and it says if f is differentiable at g of x, that's what it means. In order for the chain rule to work, f has to be differentiable at, if we're trying to find the derivative of f of g of x. You know what? Backtrack from what I just said. Let's do a much simpler example to elucidate what I'm saying. All right. So, all right. So, do you like the idea of thinking of f of g of x as like a big machine that takes in x, it goes through the g port, spits out g of x, and then g of x goes into the f port and spits out f of g of x?
Yeah, that makes complete sense to me.
Cool. So you'd agree if we wanted to find the derivative of this function, right? Then g would have to be differentiable at x.
Yep.
And f would have to be differentiable at g of x. Otherwise, we can't find the derivative of this entire machine if we can't find the derivatives of the individual ones.
Uh-huh.
All right. That's exactly what the textbook definition is saying. Our function f has to be differentiable at the point u of x, or sorry, at the point g of x. And g has to be differentiable at x. Otherwise, we can't find the derivative of the whole function. Do you get why this criteria is necessary for the chain rule to work?
That definitely makes sense.
Cool. And don't be afraid to tell me if things need a little more reiteration.
Okay, I will. But that does make sense.
Cool. All right. So if f is differentiable at g of x and g is differentiable at x, then the composite function f of g of x is also differentiable at x. That just means if the two criteria are satisfied, then our entire then we can find the derivative of our entire function with respect to x, which makes sense. If the individual derivatives exist and we can differentiate the individual parts, then we can find the derivative of the entire machine.
Yeah, okay.
Okay. So then the entire machine f of g of x is differentiable at x, and this is just the chain rule. The derivative is f prime of g of x times g prime of x, or written in Leibniz notation is this. And yet again, it says what I said, u is g of x. Uh-oh. All right. So what I want you comfortable with is you can read this textbook definition and go like, yeah, it makes sense. Yeah, it makes sense. I could read this and understand exactly what it's saying.
Yeah, I fully get that.
Cool. All right. So at this point in the lesson, what I want you comfortable with is reading Leibniz notation.
I'm good with that, yeah.
All right. And I'm going to reiterate the points, but I really want to make sure we understand this. The idea of taking the derivative of a function with respect not to x, but to some other function, g of x.
Yeah. Uh-huh.
All right. And then also, I want you to at least now understand the chain rule better than you did before you came in.
Yeah, I think I do.
Cool. At least you can understand the individual parts, right? You know what f prime of g of x means. Before today, you probably didn't know what that meant.
Yeah, it was a little fuzzy, but now it makes sense that it's like that it's like coming from another function.
Exactly. Yeah. The visual representation would be, right, if you graphed f of x as your f of g of x as your outputs and g of x as your inputs, f prime of g of x would be the derivative of that function you've drawn.
Yeah, that makes sense.
All right. And g prime of x is just if you graph g of x with respect to x, g prime of x is the derivative of the function you draw there.
Yeah.
And you might not remember the exact process, but I at least hope you can understand why the derivative of the entire function f of g of x is equal to these things multiplied. Because we did the diagrams and we did the math to show that the slope of the first function times the slope of the second function is the slope of the entire function graphed as with x as its input.
Yeah.
Okay, cool. All right. Any questions before we move on?
I think I'm all set. I think we're good.
Good. All right. This is the last topic of today. Don't be worried. We are not calculating the derivative of this function. I've just included it as an example to elucidate my point. So we now know a lot of derivative rules. And by the end of tomorrow, we will know all derivative rules. All right. With these rules, we can truly find the derivative of any function, no matter how complex. It may be hard, but we can. I once heard that taking the derivative of a really complex function is like peeling many layers of an onion. But if you know how to do it, I promise you can do it tear-free. That was a terrible attempt at a joke.
I like it.
All right. For example, let's say we wanted to find the derivative of this crazy function. We're not going to do it, but we can at least imagine what we would do if we did do it. All right. So we don't know how to calculate the derivative of square roots yet, but we will. We will tomorrow. All right. And we don't know how to calculate the derivatives of powers of fractions. We don't today, but we will tomorrow.
Okay.
All right. So if we want to find the derivative of this function, we're not going to do it. But I feel like at this point, if we really think about it, we could at least know how to do it.
Yeah.
The fact that yep.
I'll make a guess that it's going to be like the same way that you would solve it in pieces using like PEMDAS or whatever equivalent you use. Like you just like take it step by step. So,
yeah,
like,
exactly.
You know, like parentheses first with the squared. And just like kind of like doing it in chunks.
Exactly.
Like, order of operations. Right?
Exactly. So, for example, let's evaluate the first part, right? So obviously, at the biggest level, this function is the sum of two functions, right? It's this crazy function plus this crazy function.
Yeah.
So we know the sum rule is going to be involved. Let's look at one individual point. It's the ratio of two functions, right? So we're going to have to use the quotient rule to find the derivative of this function. But if we use the quotient rule, remember in the quotient rule, we have to find the derivative of the top and bottom one.
Yeah.
Right? So then we're going to have to find the derivative of the top one, which involves the product rule. So do you see how we're kind of like peeling many layers back? And then if we want to find the derivative of a product, well, then we're going to have to use the chain rule because there's a squared here and a function inside. And then we're going to have to use the power rule and all that stuff. So do you see how it's like peeling many layers back?
I definitely do, yeah.
All right. But I hope you can at least realize that if we were to go through this, we could still, with the rules that we have and the rules we will have tomorrow, we could definitely find the derivative of this function. We just have to peel the layers back.
Yeah, this doesn't look like too out of reach. It would take a while, but like we know how to do exponents. We know how to do like plus and minus. Like it looks,
Yeah, and once we know square roots and fraction powers, you'd be able to find the derivative of this 100%. And also, here's a little cool preview. What can we rewrite? Can we rewrite the square root as a power?
Yeah, that's what I was thinking. As 1/2.
Yeah, exactly. So if we found the power rule for all real numbers, it would also work for square roots, right?
Oh, does it?
Yeah, because if we found, so right now we have the power rule, and it only works when our numbers are either negative whole numbers or positive whole numbers. That's all we've proved so far.
Yeah.
But tomorrow we're going to prove the power rule for all real numbers, for any number.
Okay, cool.
All right, and I hope you can see that when we do that, we can then calculate the derivatives of square roots, because all a derivative is something to the power of 1/2, and 1/2 is a real number, so the power rule will work.
Okay, gotcha. That makes sense. Cool.
Awesome. All right, that's all for this part. And then it explains that tomorrow or the next lesson, we're going to do the remaining derivative rules, log functions, exponents, inverse trig functions, and the power rule in its full form. And we're going to discuss this amazing topic called implicit differentiation. And then we'll be done with the longest unit in the entire textbook.
Nice.
So although it says have an amazing day, we're still here. So we're gonna move on to the next slideshow after we take a break. I think a break is in good order.